were talking about in the last video the address translation. I told you that the virtual address, which would be the generated by the programmer, we will be having a page table, and using that we will convert into a physical address, right? So the CPU is trying to access a virtual address. So the page, if it is not in the DRAM, then it will be on the hard drive. So a page fault would be triggered. If a page fault is triggered, the OS would take control and find the page on the hard drive, and OS load the page into the free physical memory slot, and CPU try to access. Now it is succeed. So what happened is CPU is trying to access a page which is present in the virtual address. Now if the page is not present in the DRAM, it will look in the hard drive, so that a page fault would occur. So the OS, what it will do is that OS would take control of it. Whenever a page fault occurs, the OS takes control and it would find the page on the hard drive from the hard drive, and it will put that page, load that page into a free physical memory slot, and the CPU would now access. Now it is succeed. The CPU is now trying to now tries to access. Now what happens is that now it basically succeeds. So page fault is what? Page fault is in the virtual memory is equivalent to what? The cache miss. Let us say the cache miss, it is equivalent to cache miss. So CPU is trying to access some virtual address, and the page, if it is not present in the DRAM, a page fault is basically occurred. Now a page fault occurred, so whenever a page fault occurred, the OS would takes the control. Now if when a page fault occur, and it will find the page in the hard drive, and OS would load that page into the physical memory. Okay, now you can access it from the physical memory. Okay, so what happened is that now analogs, you can block we are going as page, block size is page size, block offset is page offset, miss is page fault, tag is the virtual page number. Virtual page number is the tag that you have to understand. So in the virtual address, some of the virtual address in the virtual address would be there in the physical address, and some of them would be present in the hard drive. That you have to understand. So there is an address translation, means this virtual address I have to convert into what? The physical address. In fully associative cache, we know there is no conflict page fault would occur, because to avoid page fault caused by the conflicts, any virtual page can map to any physical page. So in other words, physical memory behaves as a fully associative cache for virtual memory. You have to understand that any virtual page can map to any physical page to avoid page fault which is caused. So here physical memory can behave, this physical memory can behave like a fully associative cache, that if any virtual page came, that can map to any physical page. Okay, that is in direct map to set associative cache. What happened is that a conflict miss basically happened. Why conflict misses happen? Because multiple addresses are competing for the same set. So virtual memory avoid this entirely. Any virtual page you can place it to any physical page frame, just like fully associative cache. Okay, where any block can go anywhere like that. This can eliminate what? The conflict based page fault can be eliminated here. Why we are not using any comparators like fully associative cache? In a conventional fully associative cache, each block has a comparator, so that it checks the most significant address bits against the tag to determine the most significant, that is tag, it will check, right? So everyone, there was a comparator to check. But in a hardware fully associative cache, every single block has its own comparator circuit that simultaneously check if the requested address is matching that particular position. And all comparison happen in parallel. That's how hits are basically formed. But in virtual memory system, each of these physical page would need a comparator to check the most significant virtual address bits against a tag to determine the virtual page maps to the physical page. Here what happened is that each of the physical page would need what? The comparator to check. So here the physical page, I don't know, there is one image. Physical page would have comparators. Now what happens, there are too many pages. A realistic virtual system has so many physical pages. So each of the physical page, we told there would be a comparator. But what happened, there are too many pages, so that we have to provide comparator for each of the page, and that would be what? Expensive. That would be expensive, because lot of hardware is needed. So in order to prevent that, the solution is the page table. Page table is an entry which contains a physical page number in RAM and on hard drive. That means the virtual pages physical page number would be present in that page table. So it's instead of comparator, what we are using is a page table. That is, a virtual memory uses a software data structure. It is using this software data structure that is called as a page table, that is stored in the memory, and it works like a lookup table. So it uses a software data structure that is called as the page table, which is where it is stored. It is stored in the memory, and it would look like what? A lookup table. It would look like a lookup table. So instead of this, instead of putting parallel hardware components, because when there are too many pages, we need too many comparators. Each of the physical page would have comparators in them. Now what is the problem here arises because of that is that the virtual memory uses a software data structure, that is a page table, which is stored in the memory, and it would look like what? A lookup table. So virtual memory is using what here? A software virtual memory. So now uses what? So here you have to understand, they would use a page table here. So in that page table, you have to understand they are using a page table. In that page table, each of the virtual page number would have its corresponding physical page number, or if it is not present, then that means it is present in the hard drive. It is present where? In the memory. It is a software data structure. This, try to remember the word software data structure in order to solve the problem of multiple comparators. Now two-step memory access. Now we have to understand here another problem arises. Each load or store instruction requires a page table access, which is, if you wanted to do a load or store, I need to first take the page table, right, for getting the physical memory access. So the page table access translates the virtual address used by the program to physical address, and the physical address is then used for reading or writing the data. So what happens is that two times I am accessing the memory. The first time is that I have to convert this virtual address into physical address by looking the page table. So one time the memory is accessed, and the second time is that this physical address. That physical address I have to, from that physical address I have to take the actual data. So two times the memory operations are happening. That is step 1. We split the virtual address into virtual page number and page offset, and use this virtual page number to index the actual page table and get the physical page number. Then combine this physical page number with the page offset to get the physical address. So how we are getting the physical address is that the virtual address contains a VPN or offset. Now in the page table, we will use this VPN as the index and find the corresponding PPN, that is a physical page number. The offset would be same, so that you are going to combine it with the offset. Okay, so you get the physical address. So this is by looking at the page table, you get the physical page number. So you have understood that two times you are accessing the memory. So what happened, since every memory operation now takes twice as long, because I have to first look at the page table to convert into the physical address, then I have to go and access the read and write operation from the actual memory. So what happened is that the 2 full RAM access instead of 1, this would cut the memory performance in half without a solution. So because of this, this becomes 2 times slower, because 2 times our memory is basically accessed. So 2 times a memory access is happening per operation. So to fix this problem, we are creating this TLB, that is the translation look aside buffer. Translation look aside buffer is like a cache. It's like a cache which stores the most commonly used page table entries. Okay, so translation look aside buffer is what? It's like a cache which is storing the most recently used look aside. The most recently used page table entries would be present in that TLB. Okay, that is, it would be translation look aside buffer. Caches the most commonly used page table entries. We have to understand that this TLB is small. Okay, it's hardware cache that stores the recently used page table address. So page table lookup steps now would be that when you get the virtual address, we will first check the TLB. If it is present in the TLB hit, you get the physical address. If it is not present, then it will be TLB miss. Now when TLB miss occurs, we are going to the page table in the RAM, and we will get the access. We can actually get the actual data from here. So if you have TLB hit means what? The translation is done in 1 to 2 cycles, no RAM access needed. TLB miss means what? Must access the page table in RAM slower but updates the TLB for the next time. So there is TLB hit and TLB miss. TLB hit, then the translation can be done in 1 to 2 cycle, no RAM needed here. TLB miss means what? Must access the page tables in RAM slower but update the TLB for next time. So there is TLB hit and TLB miss. TLB hit means what? TLB hit means that the translation is done in 1 to 2 cycle, no RAM access for page table. TLB miss means what? Must access the page table in the RAM. It is slower but updates TLB. That is, whenever we access a new page table entry from the page table, when TLB miss happens, like the cache that updated, you should put it in the TLB also, like how we did in the cache. Then you will get the actual data what is required. Okay. So TLB is like cache here. Cache's page table entry is the TLB. Now let's talk about address translation in detail, because that is where the numerical question can come about address translations. Translation, if you think that the computer must translate these virtual address to either to find the address in the physical memory or find a page fault and fetch the data from the hard drive. So when I am translating the page, I would get a PPN. If I got it, then the page is present in the RAM. If the page is not present in the RAM, then it is page fault. The OS would take the control. Page fault means it would trigger the OS. Now OS would take the control and it will load that from the hard drive to the RAM. Understood? So physical address return, if you are getting page in the RAM, you can get the physical address directly. Now we have to understand memory. The whole physical memory is divided into pages. Virtual memory and physical memory both are divided into different pages. These have some size. These pages have some size. This is a fundamental unit of transfer between the hard drive, RAM and the address space, just like cache blocks unit of cache or RAM transfer. So like that, here the basic unit of transfer is page. Page is what we are basically transferring here. So the transfer here happening is the page, that is happening between the hard drive, RAM and the address space and also the most significant bit here would be the page number, and here the most significant bit of the virtual or the physical address specifies virtual or the physical page number, and the least significant bit would be my page offset. The least significant bit specify the word within the page and are called as the page offset. So inside the page, I found the page. Now inside the page in which word it is present, that is noted by the page offset. Now that page offset would be same in both the virtual address also and in both the physical address. In both the address, that page offset would be same. So the lower bit would specify the exact location within that page, how far into the page the data is there. This is called as page offset. Crucially, the page offset is identical in both the physical and the virtual address. Only the page number needs translation. So page number we need to translate, but page offset would always be the same in both the cases. Okay. Now virtual memory, if I'm considering, if I'm having, let's consider this numerical. I'm going to understand this numerical with you. So in this numerical, it says that virtual memory is 2 GIB, means it is 2 into 2 raised to 30. GIB is 2 raised to 30 bytes. So total 2 raised to 31 bytes. If it is 2 raised to 31 bits, that means total virtual memory have 31 address bits in it. Now physical memory is 128 megabytes, means 128 into 2 raised to 20. This is 2 raised to 7. So you get 2 raised to 27. So total 27 bits are there for the physical memory. Fine. Page size is 4 KIB, means 2 raised to 2 into 2 raised to 10, that is 2 raised to 12. So 12 bits are for the page size. Page bit offset is 12. Now if the page bit offset is 12, if the page bit offset is 12, the virtual pages would be how much? How much would be my virtual pages? Virtual pages you can calculate the total virtual memory divided by the page size. See, virtual number of virtual pages available, the number of virtual pages available would be equal to the total virtual address, right? The total virtual capacity, how much, divided by that page of that is the page size. Similarly, total number of physical pages, how can you calculate? The total number of physical pages is the, oh sorry guys, some problem, I reached to the starting slide. We were talking about this numerical. Okay, so here you have to understand the total physical page, the number of physical pages is equal to what? The number of physical pages would be equal to the number of what I was talking about. Okay, the number of physical pages is the total physical memory available, right? The total physical memory available, that divided by the page offset. Page offset. Okay, 1 minute guys, just excuse me for 1 minute. Okay guys, sorry for the time. Okay, now this we taught. So virtual pages, the total virtual memory is 2 raised to 31. So 2 raised to 31 divided by the page size, that is 2 raised to 12. If I do, I get the total virtual pages. Similarly, total physical pages I can get, the total physical memory is 2 raised to 27. That if I divide with the page size, that is what, 2 raised to 12. If I do that, then I will get the number of physical pages. Okay, and then the 2 raised to which bit means the 19 bits are for the virtual pages, and physical pages you have 15 bits. 2 raised to 15 means that 15 would be the number of bits there. Understood? You are taking log here. Fine. So when you look at this particular part here, you are given a virtual address. So let's say you are given this address to you. Okay, this is one virtual address that is given. Now this address, if I'm taking the address, virtual page number is given to us. This is the and the physical this is physical memory, and this is the virtual memory. Okay, so a corresponding, if I'm saying that let's say my address is 0x535f8, this is what my virtual address. So I told you that my virtual address would be how many bits that I calculated. My virtual address is 31 bits. So I'm writing this 8, I write this would be my 8 value, f I write this, 3 I have written here this, and 5 I have written this. And now what I have is that the total 31 bits I needed. Okay, total 31 bits I needed. So here 0, 1, 2, 3, 4, 8, 9, 10, 11, 12. But it will be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 3 more bits you have to write, because 30 bit it would be. Okay, from there I'm telling you that the last bits, that is the last 12 bits I told you, last 12 bits are my offset bits. So here if I'm taking, these are my offset bits would be what? Offset bits would be this last 12 bits, and the rest of these bits would be my VPN. Okay, VPN. That means it is 0x5. Now in that 0x5 location, you have this virtual address with you. Okay, 0x virtual page number, you have physical page what? This is mapping to physical page 1. So that means virtual page 5 you got, that would map to physical page 1, means that one's address you have to write here. So ppn plus offset, if you do ppn plus this offset, if you do, you're going to get the final physical address. You're going to get the final physical address if you do ppn plus the offset. You have to remember this values here. Now one important thing that I wanted to teach here is that you are going to say that if a virtual address this comes, their corresponding this would be my physical address. Now how I am going to get this physical address is what I am going to tell to you right now. So that means if I am having, let's say 0x53f8, okay, I will just explain it again. 0x53f8 I am having. So that means this is my virtual address, and I told that virtual address is how many bits? Virtual address is 31 bits. From the table, this table, from which table we got this? From this table. Virtual address is 31 bits.